In this video, I am going to explain about design and simulation of domino and NORA logic using Tanner EDA version 2019.2. So this is a structure of the domino logic used for our design. In domino logic, there is no PMOS section. Only there is a pull down section, that is NMOS section will be there. So in this there will be a clock signal will be used. In clock signal there are two modes, evaluation mode as well as pre-charge. So from here we are taking the output and there will be inverter will be connected. Then we will be taking the primary output. If it is multiple stage means this will be repeated like this. So this is a structure of domino logic. So in our example, I am going to take the structure of AND gate. Here I have designed AND gate using domino logic. So I have represented AND gate AB. Here in NMOS it is series combination of two NMOS transistors. Then clock will be applied to this PMOS as well as NMOS. The output will be tapped from here. It is connected to the CMOS inverter or NOT gate. The input A and B are applied in between these two NMOS transistor. Output C is connected in this inverter. The clock is applied in here. I am applying as a pulse. Next we can see about the response of the AND gate domino logic. Here we are using the A and B are input, C is our output, and the clock is the another input. So in this first stage, this off stage is considered when clock equal to 0 means it is considered the pre-charge mode. When clock is high means it will be considered the evaluation mode. So in the evaluation mode we have to check the output. In pre-charge mode, whatever the input available it will be captured and it will give the response at the evaluation time. Here for input 1 1 we are getting output will be also 1 for AND gate. So remaining for all other input the output will be 0. For in this case that is 1 0 and in this position 0 1 and 0 0 we are getting output will be 0 at the evaluation phase. So next we can see how to design domino AND gate using Tanner EDA with SEdit. First double click the SEdit. SEdit open. First go to File, New Library, Browse, create a folder, My Domino. Click OK. Then right click, add library, browse, go to the folder generic underscore 250nm. In that generic underscore 250nm devices. Click OK. Then right click, add library, browse, go to the folder standard libraries, add the folder MASC, click OK. Again right click, add library, browse, go to the folder spice underscore plot, click OK. Again right click, add library, browse, go to the folder spice underscore source, click OK, click OK, then go to cell, new view, click OK. So this is the area we are going to draw our design. First select the library, generic underscore 250 nm, select the PMOS transistor, pick it and place it here. Here in our design we need one PMOS transistor. Then I'm going to take the NMOS transistor. So this is for the applying clock for pre-charge and evaluation. Next, for representing logic in NMOS, we need to represent AND gate, we need 2 NMOS transistor. For this I am keeping 2 NMOS here. Then click done. Then maximize this screen, fit to screen, press home button. Then take the wire, connect these transistor, here we are applying the clock pulse. This is for A input, this is for B input. Next, in the output of the domino logic, there will be inverter or CMOS NOT gate. Here I am directly taking the NOT gate. So the NOT gate is available in the library, generic underscore 250 underscore logic gates. So for that, right click this, add library. We have to add one more library for that. Go to the folder generic underscore 250 select the folder generic underscore 250 underscore logic gates. Click OK. Now it is added. Here select the library inverter, keep it here. Take the wire, connect this output in this section. From here we will be taking the primary output. First take the port A, there is input port. This is for clock. Click OK. Go to spice source. We need V pulse. Pick it and place it here. So we need for input A, we need one more pulse. For input B, we need also one more pulse. Pick it and place it here. Then go to MISC, select the ground. Instance, connect one ground here, so another ground here, another ground here, here one ground required. For giving VDD, we need one more ground. Next, take the input port, pick it and place it here. Name it as A. Next, take one more port, place it here. Name is B. Click OK. Next, go to MISC, select VDD, instance, click here, then take the output port -C. Then go to spice source, select the PDC source for applying VDD. Then we need one more VDD thermal. Copy and paste it here. Next, take the wire, give this connection for this clock. Next, for printing their output, we need to place some print voltage command. So pick it. For displaying clock, we need this one. For the input, for another input, for output, we need print voltage. Next, for input signal, we need to make some changes. Select this B. So I am giving the pulse as 100. Next, for this clock signal, I am giving pulse period is 100 nanosecond. So initially I need the clock as low signal. So by default it is initially high pulse will come. For making it slow, I am giving a delay of 45 nanosecond. Next, our circuit is over. Next, our aim is we have to set up the simulation. For that, click the setup simulation. Click general, add the library, browse, select the library name generic underscore 250nm.lib, click open, go to the end of the location, type TT, then click this transient analysis, give the time being 400 nanosecond and the maximum time step is 4 nanosecond. Then click OK. Then click Start Simulation. So this is the simulation status from the T-Spice. Simulation is completed. Next waveform came. So expand this screen. So you see here A, B, this is your output C. This is your clock input signal. So this is the pre-charge mode. In pre-charge mode, it will get the input. Now input is 1 1. For this AND gate, input 1 means output will be 1. So in the evaluation phase, this is evaluation phase clock, we will be getting output. So next, in this pre-charge mode, now input is 0 1. So output will be 0 for AND gate. So in this evaluation mode, we will be getting the output as 0. Similarly, it will be repeated for all the possible combination of inputs. This is a waveform for the domino logic with transient analysis. Next, we can see NORA CMOS logic. NORA means no race. So normally in NORA CMOS logic will be used in the pipeline structure implementation. So this is the structure of the NORA logic, NORA CMOS logic. Here the PMOS connected to VDD and this NMOS is underground. In between will be having the NMOS logic, that is pull down logic will be there. Then next it is followed by there will be a pull up logic. Here we will be giving the complement of this clock signal will be provided for this section. Then at the end of this next it is followed by again there will be NMOS section, then PMOS section, like that it will be continued. And finally we will be having the C square MOS logic structure at the end of the section for getting the output. So next we can see for NORA CMOS logic implementation for the function a plus b whole bar into c plus d whole bar. For this logic I have drawn this schematic diagram. So first we have to represent this logic. First take the a plus b bar. In this a plus b bar, to represent this to represent a plus b bar in NMOS logic, two NMOS transistors are in parallel. Here we will be having PMOS and NMOS. It is connected to the clock. Then for next section we have to take output from this position. Then we have to represent this C plus D. C plus D it is in the form of PMOS. So in PMOS C plus D means it is in series. So the C plus D is in parallel with this A plus B bar. So this output is given to this gate PMOS section and it is parallel to the C plus D. Then we are taking output, tapping this section out from here. Then we will be connecting this C square MOS logic. So this is the structure of this NORA CMOS. For this function, out is equal to a plus b whole bar into c plus d whole bar. So next we can see the output of this logic a plus b whole bar into c plus d whole bar. We are having the input A, B, C as well as D. Then we will be having two clock signal and we will be getting the output like this. Here also there will be a pre-charge and evaluation mode. In evaluation mode we will be getting the output. We have to give the clock like this structure. Then we will be getting the proper output. So next we can see how to draw the NORA logic in SEdit. So double click the SEdit. That is open. Go to File, New Library, Browse. Open a folder, My NORA. Click OK. Click OK. Again right click, add library, browse, add the folder generic underscore 250nm underscore devices, click OK. Again right click, add library, browse, generic underscore 250nm underscore logic gates, you can add. Then click OK. Then right click, add library, browse, go to the folder standard libraries, in that select MISC, click OK, and click OK. Again right click, add library, then browse, go to the folder spice underscore plot, and click OK. Again right click, add library, browse, select the folder spice underscore sources and click OK. Then go to cell, new view, then click OK. Here we are going to implement the logic a plus b whole bar into c plus d whole bar. For representing this NORA logic, first going to take the device, generally connect 250 nm underscore devices. I'm selecting the PMOS. Instance. I'm placing 3 PMOSs. Then take NMOS. Here I want to present the A plus B in NMOS. So NMOS A plus B it is in series format. Then for second section I have to represent this PMOS. Next I have to represent in terms of PMOS for this parallel combination of A plus B whole bar into then C plus D. So in C plus D, in PMOS it will be in the series section. Then press home button to fit to the screen. Then take the wire, view the connections. Then output from this first section is given to of this section. Here there will be NMOS will be there. Copy and paste. Take the wire. So output from this PMOS section will be given to input of this final section. And here we need to NMOS. Take the wire. And take the ground. Clock. And source. Take weak pulse. Also we need this input A we need to cut for input B, for input C, for input D also we need pulses. Similarly for clock bar we need another one pulse. So take the ground, Control C, Control V, Control V, Control V, then take the port giving us A, giving name as B, C, D, This output also given here. This gate also we record output. Here we will be tapping here. Output out. Here we have to connect clock bar. Take the input port. Say clock bar. Then select the VDC. Keep it here. Control V. Select the ground. Then select the VDD. Next for printing, so one more VDD we require. Control C, Control V. For spice plot, instance. We need to print output, so here on place it here. So print C, print D, clock bar, then print A, plot the B, plot the clock. So next we have to change some settings in the input. So initially taking clock as 100. Here delay time I give it as 45. For next clock pulse 100. Pulse width is 35. Next go to setup, click transient analysis. Select the library. Go to the folder process, generative TNM, models, open, type TT, then click OK, then run simulation. this is clock bar. So this is evaluation mode, this is pre-charge mode, this is evaluation mode. So in this time we will be getting output. For now it is pre-charge mode. The inputs all are 1, A, B, C, D. The inputs are all are 1. The output will be also 1. So this is output of the logic A plus B bar into C plus D whole bar. Thank you for watching.